So integration sum of forces dt is called linear impulse. On the right-hand side of the equation, that's a term m times v2 minus v1. This term is called change in linear momentum. So if you use mass times velocity, that's called momentum, linear momentum. But now we have mass times velocity at one moment minus another mass times velocity at another moment. This is called change in linear momentum. So we're kind of subtract two things or calculate what's a change of linear momentum. So that's why the title of this section is called, let's go back here, linear impulse momentum equation, because on the left hand side we have impulse and on the right hand side we have linear momentum. So combine them together, we call this linear impulse momentum equation. Okay. There's a couple of things. Any questions about the concept linear impulse, linear momentum? Okay. All right. So when you do solve problems in this course, and oftentimes we can simplify that integration. No one likes to do integration, right? But for that term here, sum of forces dt can be simplified to average force times delta t. So if you know what is the average force, you know the time period, you can use force, the average force times delta t to find out what is linear impulse instead of doing the integration. But that's under the condition average force is given. All right, there are a few special features about this equation. The first one is if sum of forces equals 0 in a given direction, now what does that mean to the equation? So let's go back to this, look at this equation. Okay, so this is a vector equation, right? A vector equation, if we only have I and j direction, we can break this vector equation into two scalar equations, one on I direction, another one's on j direction. We can do that. But what if sum of the forces equals 0 on I direction? Now when you have in your scalar equation on I direction, you're going to have 0 on one side of equation equals n times v2 minus v1, and both v's are on I direction as well, right? So then you end up with a very simple equation, just mv2 minus mv1 equals 0. So when that's the cases, we call that conservation of momentum. This is called, if this is the case, then the linear momentum is conserved. So that's the concept in words. The linear momentum is conserved if sum of the forces equals to 0 on a certain direction. But in mathematic form, conservation of momentum, it's just mv2 minus mv1 equals 0. Or you can rearrange this as mv2 equals mv1. Okay. Same thing if sum of the forces equals 0 in a given direction, this does not imply linear momentum is conserved in other directions. Here I want to highlight does not imply. Okay, here the direction is very important. Linear momentum only it's conserved on the direction forces equal to 0. So that forces equal to 0 in one given direction doesn't imply moment conservation in other directions. Okay, so keep that in mind. There could be a true and false or multiple choice problem in your exams or quiz. Another thing about this linear impulse momentum equation is so conservation of momentum and conservation, we have another thing is called conservation of energy. Okay, now my question for you is, I want you to take 1 minute to think about this. What's the relationship between conservation of momentum and conservation of energy? Can I see if we have conservation of momentum, does that implies we have conservation of energy? Maybe let's take see this another way. If we have conservation of energy, does that imply we have conservation of momentum? Okay, here, make it very clear. Energy and momentum are totally two different things. So here, there's no relationship between those two concepts. So if you're on the exam essay, oh, this system has conservation of energy. That's why every momentum is conserved on all directions. So that's a wrong statement. Conservation of energy and conservation of momentum are totally two things. They don't have any relationship. Okay, any questions on the concept of linear impulse momentum equation? Okay, if no questions, let's take a look of an example on your book. Okay. That's weird. Gotcha. Okay. Let's look at this example, 4C1. It's on your page 236. So in this example, we're given a block A having mass of m, has an initial speed of v1. As it moves to the right on a rough horizontal surface with a coefficient of kinetic friction of mu k. As the block slides, a force Ft acts to the right of the block with the time history for Ft shown below. We want to determine what is the speed of that block at t equals delta t, and the speed of the block at t equals 2 times delta t. And we're given the values for mass, force, initial force, speed at 1, and mu k, and delta t. Okay, want you to talk to each other for 2 minutes to think about compare this example with all the other examples we did in this chapter. So what's the difference of this example? What is something we never done before? Okay, 2 minutes, talk to each other about what's something new about this example and compare with other examples. Okay, Krista, what is something different about this example? So we have a graph that shows time versus force. How come that's new? Why do you think that's something new? Never seen that before? Okay, so in section 4a, we have problems with forces, right? All the forces in that section are constant force. You never experience something, a force that's changing with time. So this is something new. A force is not constant anymore. Yeah, maybe right between 0 to delta t, that force is constant, but once you pass t equals delta t, the force decreases over time. So that's something we have to deal with, a non-constant force. Okay. And what other things you think is new? Dalton Bell? Anything for you do you think is new?
Not really.
Okay. Okay. Another thing, if you look at what we need to determine, here in this problem, asks you to find speed at 2 different time moments. We never had a question like that, right? Previously in section 4b, it may ask you to find out speed at position 2 or position 1. But we never ask you to find out speed at when t equals something, right? So that's something new. So the reason I ask you to think about this, because chapter 4b can be confusing. Once we're done with chapter 4 A, B, C, D, and if you just throw you a question, you will get confused. You're like, oh wow, we learned so many different techniques, but which one I should pick, right? But here is a sign, it's a signal to show you if this problem is asking you to solve something related to time, that probably means you have to use something we learned from this section, which is linear impulse momentum. So time, it's a signal to tell you use linear impulse momentum. All right. Now let's look at how should we solve this problem. Okay. And I know previously we always have different steps we can solve a problem, but in this section we're kind of loose on the steps. But do you guys think the steps help you to solve problems? Raise your hand if you think, yeah, I really like those steps that help me gather my mind to solve problems. No, not really. Okay. All right, but let me go through this problem. I still like solve things, follow steps. So it's pretty similar with the steps we did in 4a. I'm gonna do step 1 to draw free body diagrams. That's always the first thing of this chapter, free body diagrams. We only have one single mass, which is a block in this case. In a couple of forces, we have a F force, weight force, have a normal force. Also, it's on a rough surface, so there is friction force too. That should be the free body diagram. In step 2, it's still the same. Set up the coordinate systems. In this case, a classic I and J would be enough. Step 3, it's still the same. List all the forces in vector form. So forces in vector form. Since we have 4 different forces in the free body diagram, so write out each force in vector form. So F force should be the force on positive I direction. Weight force, it's a negative force, negative mg on j direction. Normal force, positive j direction. And friction force, it's negative mu k n on I direction. Okay, step 4. So in step 4, things are getting different. We don't need to do acceleration in this section. Instead, we just apply the linear impulse momentum equation. Okay. So the linear impulse momentum equation looks like sum of forces dt equals m v2 minus v1. Okay, here, since we have sum of forces, you want to use all the forces in your step 3, write them inside of that. Sum of the forces should equal to, we have force plus weight force, normal force, friction force, dt equals m v2 v1. Okay, so the integration here, you need to put a bound. What's the limits for that integration? In this case, the integration is respect to time. So you need to have 2 different times on your integration as limits. So if we look at the question, we want to find out the speed of block at t equals delta t. So t equals delta t, which is here. If you look at the plot before delta t, and that force, it's a constant. So that makes things very easy. So it's a constant force, and if that force is constant, the integration would just be the area under that curve, right? So it should be just the integration of, it's the area under this curve is that rectangular shape. How to calculate the area? Width times height. On the x direction, we have delta t. Use delta t times f naught. That should be the result of that integration. So let's label the 0 to delta t. Since from 0 to delta t, everything is constant, we can simplify this just as F plus weight plus normal force plus friction force times delta t equals m v2 v1. And now if you look at that, that's a vector equation. You can break that vector equation to 2 scalar equations. So the first scalar equation should be on I direction. Well, maybe before we do that, let's plug in, substitute all the forces first. So we have Fi plus negative mg, that's on J, plus N on J, plus negative mu K N on I direction. Delta T equals, and same deal, we want to break our velocity into I and J. So V2, V1, how would you write V2, V1 as something I and J? Oops. If you look at that block, it can only move on I direction. So the motion of the block A, it's only on I direction. So our velocity, V2, should only be on I direction. Plus 0J, if you want to write that, minus V1I minus 0J. So now we have a vector equation with I and J components. We can break this equation to two scalar equations. The scalar equation on I direction would give you forces minus mu K N delta T equals mv2 minus mv1. So that's the first scalar equation you can get. The second scalar equation is on J direction. We have negative mg plus n times delta T equals 0. Nothing is on the J direction in terms of velocity. So those are the two scalar equations. In this problem, we're given V1. So V1 is given, mu K is given, force is given, delta T is given. And from the second scalar equation, we can solve for what is normal force, right? So that normal force is kind of given. So everything is given besides, except for V2. So from these two scalar equations, we can solve for V2. And V2 is a speed at time equals delta T. So if we write out the symbolic solution, it's going to be delta T divided by m times force minus mu mg plus V1. This is on I direction. So V2, it's a vector. If you write that as a vector, it only has component on I direction. Now we solve the first part of this example. Any questions? Okay, feel free to plug in numbers if you want to know the exact numbers. And V2, it's about 15 meters per second. Okay. Any questions for this example so far? So it's pretty, I want you to compare this problem with all the examples we did in section 4a when we used Newton's second law. Right, the only difference here is at step 4, we applied the linear impulse momentum equation and substitute all the forces into the equation and break that equation to 2 scalar equations. Very simple. Okay. Now we have a second problem we need to solve. Here, we also want to find speed of that block at t equals 2 times delta t. So now you have to deal with the whole curve, the entire curve. Solve 2 equals delta t, which is at the end of the curve, this profile. To solve this part, the only thing you need to do is to change the limit of your integration, right? So here, that's our main equation, right? Our limits here is from 0 to delta t. Now you have to find out, you have to change that to 0 to 2 times delta t. F plus weight plus normal force plus Ff delta, dt. From what you learn in integration, we can break that, the whole range from 0 to 2 times delta t to the two sum of integrations. So we can break this to from range 0 to delta t, all the forces delta dt, plus another range should start from delta t all the way to 2 times delta t times F plus weight plus normal force plus friction force. And the right-hand side remain the same, V2 minus V1. Okay, any question here? So here, simply just break that integration to 2 different parts. The reason I want to do that, because we already solved this guy here from 0 to delta t. We know what is the answer here. And in that range, F is a constant, so everything is pretty easy. Here, the second part of this integration, if you look at look at this part, weight force is constant, normal force is constant, friction force is constant, but that F force, it's in that profile, it's decreasing over time. So we have to consider that. So it has to be integration from delta t to 2 times delta t just for that F dt. You have to solve that. So let's write that out. I'll write this. So I would just put here, rewrite that as delta t to 2 times delta t. That applies for that force F dt. But for the other forces, because they're constant, you can just write as weight force plus normal force plus friction force times delta t. Okay, any question here? Here I'm just trying to simplify that integration. I think here we can simplify this as well. Okay, now we only have one term that has integration inside, which is here. Integration from delta t to 2 delta t, f dt. If we go look at that profile here, how to find what's the result for integration for force from delta t to 2 delta t? That's just simply the area underneath that line. That's a triangle. How to find area of the triangle? Area of that triangle A equals the base length, which is from delta t to 2 delta t. So the length should be just delta t times the height, which is f naught times 1/2. So it's 1/2 base length times height. So that would be the result for that integration. So you can put that back to the equation. Go here. And from this equation, maybe we should change this. Instead of call this V2, we should call this V3. From here, we can solve what is V3. That's a speed at time equals delta 2 times delta t. If you plug in everything, we'll write out the numerical solution, and it should be around 15.16 meters per second I direction. All right, that's all for today.